for our last example in this section, this type of problem is a little bit different. We're going to use the graph of f prime of x. So the thing we want to keep in mind is this is the graph of f prime of x. And we're going to use this graph to help us sketch a possible graph of our function f of x. So we're not actually starting with an equation. We actually don't have any sort of equations here. All we have is this graph to work with. But we can take a lot of the skills that we used when we had the equations of functions and apply them here as well. If you think about if I wanted to sketch a possible graph, thinking back to the examples that we looked at earlier, we started by thinking about where are our local extrema? Where is this function increasing and decreasing? And in order to find those things, we need to find the critical numbers. So first thing I'm going to look for are the critical numbers. And remember, critical numbers occur at places where f prime is equal to 0 and at places where f prime does not exist. Those are the two things that I need to remember. So if I think about places where f prime is equal to 0, I'm thinking about, again, this is the graph of f prime of x. This is not the graph of f of x. So at places where f prime of x is equal to 0, well, let's say if I look at this part of my graph right here, f prime is negative on that because it's below the x-axis. And if I were to look at, say, this part right here, that part, f prime is positive because it's above the x-axis. So if we want to think about places where f prime is equal to 0, we want to know where does it cross or where does it touch the x-axis. And I see it at those 2 points right there. So it looks like 1, 2, 3, 4, 5. So right here at -5, and then at 1, 2, 3 right here. So our critical numbers here are x equals -5 and x equals 3. The other case we need to consider is places where f prime does not exist. And just by looking at the graph of this, it doesn't appear that there's anywhere that f prime does not exist. So we don't really need to worry about this particular case in this problem. So we have our two critical numbers. We've got x equals -5 and we have x equals 3. So that's great. And we think about, okay, what did we do next after we found our critical numbers? Well, we made a little number line to help us. We said, here's f prime, and we'd say, here's -5, here's 3. And remember, we found these by taking the derivative and setting it equal to 0. So I'm going to put a little 0 above each of those, and that's going to be helpful because remember, when the derivative is equal to 0 at those points, that means that I have a horizontal tangent line at those two x values. So now I'm going to go ahead and, well, my next step would have been to plug numbers into the derivative, but we're kind of at a loss here because we don't have a derivative to plug things into. But I do have the graph of the derivative. So I can just look at the graph, and that's actually going to tell me whether my derivative is negative or positive. So let's say we want to work with this left-hand side first. We're going to work with the left-hand side of -5. So if I look at the left-hand side of my graph over here at -5, I want to ask myself, are these y values, because again, these are the y values of f prime of x, are these y values negative or are they positive? Well, those y values are negative. Those belong to the derivative. So that means that my derivative is negative on the left-hand side of -5. So we've got that part done. Next, I want to think about the section of my graph in between -5 and +3. So if I highlight that section of the graph, I'm talking about this part of my graph right here. And again, I'm just going to ask myself, is my graph negative or is my graph positive? Because again, this is the graph of f prime of x. Well, that part of my graph is above the x-axis, so it's positive. So I'm going to put some plus signs right above there. And then we just have one more section of our graph to worry about then. We want to think about the right-hand side of 3. If I think about the right-hand side of 3, again, I'll highlight that section of my graph. Well, all those are, again, above the x-axis. That section of my graph is positive. So that means that the derivative is positive on that interval. So I can now look at this and say, okay, based on what I found right here, my graph is decreasing on negative infinity to negative 5. It's increasing on negative 5 to 3. And then it's increasing again on 3 to positive infinity. So at x equals negative 5, at this point right here, it changes from decreasing to increasing. We've got a horizontal tangent line, and we can see, well, we're going to have a local minimum at x equals negative 5. At 3, it's actually a little bit trickier. That if I were to draw in the behavior that we're going to see here, it's increasing, but we have to remember that there's going to be a horizontal tangent line there. So it's actually going to be increasing, and then it's going to level out almost like there's going to be a maximum there. But then if I look at the right-hand side, it's increasing and not decreasing. So instead of going down, it's just going to continue to go back up. So I should still see that horizontal tangent line there at x equals 3. And we'll draw that in just a moment. So I have, at this point, everything I need to sketch a graph of this function. Now, one thing I want to point out here is I said we want to sketch a possible graph of f of x. We actually don't know what the actual graph of f of x is because I'm not going to be able to find the y values here. I'm not going to be able to find the y values of like my local minimum here. So you can actually place those points as high or as low as you want to. So I might say, okay, here is 1, 2, 3, 4, 5. Let's go ahead and say at x equals negative 5, I'm going to place my local minimum right here. And again, I'll remind myself that at that point we have a minimum. And then I'll also draw in my horizontal tangent line. Let's do that. So I can draw in that part of my graph. It's decreasing. Oops. Decreasing hits that horizontal tangent line, then increasing. And then once I get to x equals 1, 2, 3, we need to have another horizontal tangent line, which means my graph is going to start to level out. So I should see another horizontal tangent line here at x equals 3. But then again, instead of decreasing and us having a local maximum, we said that wasn't a local extreme value. So in this case, it actually just continues to increase after that. So this is what the graph, or a potential graph of f of x would look like. Now, the y values don't particularly matter as long as we have the correct behavior at the same x value. So you could actually take this graph and shift it up, or you could shift it down. You could take this whole graph and shift it down and draw something that looks like this. This also would have been perfectly correct. You could have taken the same graph and shifted it up. This also would have been perfectly correct. So take your time with these problems. They are very different, but it is a good practice to think about what does the derivative tell us about our graph. It's just kind of, instead of relying on equations and crunching numbers like we've been up until this point, we have to look at a graph and think about, okay, what does this graph tell us? In this case, this is the graph of f prime of x. It tells us the sign of the derivative, which then we can use to find local extrema and then sketch the graph of our function.